Hello, everyone. Welcome to another lesson on physics. Today we are starting on our unit on Newton's laws and force. So we're going to be talking about push and pull. So you may have heard about the force in Star Wars, but that's not the exact same force that we're going to be talking about. Okay. So when we say force, this is a word that we use all the time in our vocabulary. But what are we really talking about? What is a force? So let's look at an example here. So we have a bowling ball above that sits motionless on a table. So what would you have to do in order to make it move? Because it's just going to sit there if we don't do anything to it. So what we'll have to do is either apply a push or a pull, and then it should start moving. So force is simply a push or a pull on an object. Force is a vector, so that means it has magnitude and direction. So just like velocity, acceleration, displacement, it is another vector. So if it's unbalanced, this will change the state of motion. We have a couple different types of force. A contact force, which is a physical interaction between objects. So some that we'll see are the normal force, the tension force, friction, or just some examples as we'll get into. And the other type of force is called a field force. And this is an action over a distance. So some examples are gravity, which we also call weight, magnetic force, static electricity. All these are forces that you don't have to be in actual contact with them for them to occur. So let's take a look at Newton's laws. So Newton's first law states that an object at rest remains at rest and an object in motion continues in motion with constant velocity. That is, constant speed in a straight line, unless it is acted on by an unbalanced force. So we need a force to change its state of motion. If it's at rest, it'll stay at rest. If it's at motion, it's going to stay in that motion, that same velocity, unless we apply a force. So this is also known as the law of inertia. That's another name for this. So I think many of us may have heard the word inertia before, but maybe not quite in the right way. So inertia is the tendency of an object to resist a change in motion. And this is directly related to its mass. So do these guys have a lot of inertia? These two sumo wrestlers? And the answer is going to be yes, they do have a lot of inertia. The bus has a lot of inertia, but a mosquito with not a lot of mass does not have a lot of inertia. So more mass is going to mean more inertia. So this is to say that more inertia means more resistance to a change in motion. So it's harder to stop or harder to start. So we can think about this of if you're going to stand in front of a school bus and try and stop it, you might not have a lot of luck. But if someone throws a volleyball at you, you should be able to catch it and stop it, no problem. So what exactly is mass? So mass is the amount of matter contained in an object. So the mass is going to remain constant. It doesn't matter where we put our object, is going to have the same amount of mass. You can put the school bus into space and it's still going to have the same amount of mass. So this is a property of an object that does not change. And this is going to depend on a couple things. So the size or volume of an object, as well as the density of the material that makes up the object. So you can have something that's very dense and small have the same mass as something that is large but not very dense. So let's take a look at an example of inertia. So you might get asked something like this. So which object has the greatest inertia? And something we need to take into account when we're talking about inertia is this is completely based off of something's mass. It doesn't matter if it's moving, staying still, where it is, it's still going to have the same inertia. So we have a softball in flight, a motionless student, a falling leaf, and a helium-filled balloon. So the one with the most mass is going to have the most inertia, and that is going to be a motionless student. So this only depends on mass. The greatest mass has the greatest inertia. It's as simple as that. So let's take a look at an example that has some numbers. So we have these 4 objects, different masses, different velocities. So which one is going to have the greatest inertia? The answer is going to be 5 kilograms. A. It has the greatest mass, greatest inertia. Doesn't matter how fast it's going. Inertia only depends on mass. So this is where it's a little bit different from maybe how some people use inertia in everyday language. Now let's talk about net force. So net force is the vector sum of all forces acting on an object. So the net force is 0 if the object is motionless. So this is a static equilibrium that's just staying in one spot. Moving with constant velocity. This means dynamic equilibrium, that it is moving but with a constant velocity. So this means that if all forces are balanced in every direction, then the net force will be equal to 0 newtons. If forces are not balanced, then our net force will not be equal to 0 newtons. It'll be equal to something greater than or less than 0 newtons. And if this is the case, then there will be some sort of acceleration. So this is Newton's first law, that an object remains at rest and an object in motion remains in motion unless acted on by some unbalanced force. And then this other part down here is Newton's second law, that an unbalanced force will cause a mass to accelerate. So let's take a look at what Newton's second law says. So it says that the acceleration of an object is directly proportional to the net external force acting on the object and inversely proportional to the mass of the object. All right, a lot of big words, a lot to unpack from there. Pretty much it's saying exactly what this formula below is saying. Acceleration equals the net force divided by the mass. So what we'll see, a larger net force should result in a larger acceleration. But depending on the mass or the inertia of it, this will decrease our acceleration. So they kind of act against each other. So a lot of force on a light object, a lot of acceleration. A large object with a smaller force will be a smaller acceleration. So this is our equation. And the unit of force is the Newton. And the Newton is a derived unit. So what we'll see is that force is equal to acceleration, which has the units of meters per second squared. Net force has the units of newtons, and mass has the units of kilograms. So if we take a look at the units, we'll be able to multiply mass over to the other side to see that force equals mass times acceleration, or F equals ma. So if we take a look at the units, it'll be newtons equals kilograms times meters per second squared. Or we could say kilograms times meters over seconds squared. That's what a newton is. And it being a derived unit means that's made up of other units, unlike mass or distance or time, which are their own units. So another way to remember the law and the equation, an unbalanced force causes mass to accelerate. Or in other words, F equals ma, which we can see right here. Force equals mass times acceleration. All right, let's take a look at an example of using our new formula. So a motorcycle and its rider have a combined mass of 275 kilograms. So that'll be one of our first givens. Mass equals 275 kilograms. The biker slows his motorcycle with an acceleration of 4.5 meters per second squared. So our other given is going to be our acceleration of 4.5 meters per second squared. And if we assume that the biker is going forward, then we can assume the acceleration will be negative. But we're just going to talk about magnitudes here because it all depends on which direction we say is positive or forward. So what is the net force on the motorcycle and rider? So we can use our formula that we mentioned before. F net equals mass times acceleration. So we can plug in our numbers. F net equals 275 kilograms times an acceleration of 4.5 meters per second squared. And from there, we can get our answer that is equal to 1,237.5 newtons. So we must remember our units of newtons, which we'll represent with a capital N. All right, so let's take a look at another example. So a force of 20 newtons east and a force of 20 newtons west act concurrently, which means they're acting at the same time, on a 5 kilogram block. So find the acceleration on the block. So what we'll want to do on this one is take a look at the forces acting on the block. And what we're going to do is draw out something called a free body diagram. And we'll talk about this a little bit more when we get to it. But we have these two forces, and we can look at them like vectors. So we have 20 newtons going east, and we have 20 newtons going west. So if we're talking about the net force, which is another way to say the sum of the forces, which this sigma represents the sum of, so we're going to add them together like other vectors, the same way we did with displacements and velocity. So to the east, we can call this positive, so positive 20 newtons, and then plus the one going to the west, which will be a negative 20 newtons, which will give us a net force equal to 0 newtons. All right, so the one other thing that we are also told is the mass is equal to 5 kilograms. So now we want to find the acceleration. So we can use the formula from before. Acceleration equals F net over m. And when we substitute in our units, we get 0 newtons over 5 kilograms. So what we'll see here is that since our net force is 0, our forces are balanced, we get an acceleration equal to 0 meters per second squared. So what I often get a lot is that if there's a force acting on an object, we expect some sort of acceleration. But if they're balanced, then we are going to end up with no net acceleration, no net force, which will result in no acceleration being applied. All right, so let's take a look at this next example. So this example 5. Two forces, F1 and F2, act on a block as shown below. If the block accelerates at 2 meters per second squared, what is the block's mass? So what we want to do is get our net force. So we can look at it as the sum of our forces, F net. And we're going to add together F1 and F2. So by doing this, we can plug in F1, which is 12 newtons. We'll call it positive because it's going to the right, and negative to the left. So then we'll subtract 8 newtons, which will give us a net force equal to 4 newtons. And the other thing that we're told is that the block is going to accelerate with 2 meters per second squared. And now we are looking to find the mass. So if we use our formula, F net equals m times a, we can get the mass by itself, divide over the acceleration, that F net over a is equal to the mass. From here we can plug in our numbers. Mass equals 4 newtons over 2 meters per second squared. Now something else we also want to do is we want to be able to check our units and make sure they check out. But it's really hard to compare newtons to meters per second squared. But newtons are a derived unit, which means that they're made up of other units. So what we can do is break it into what we have had it before, which is 4 kilograms meters per second squared over 2 meters per second squared. What we'll see now is those meters per second squared cancel out. We'll end up with kilograms on top. So that's exactly what we want when we're looking for a mass. So when we divide these, we will get that the mass is going to be equal to 2 kilograms. Now let's take a look at example 6. So a 0.15 kilogram baseball moving at 30 meters per second is stopped by a player in 0.01 seconds. So what is the average force applied to the ball? So let's write down some of our givens, because this one's going to be a little bit different from the ones we've done before. So it tells us that the mass is going to be equal to 0.15 kilograms. And it also tells us it's moving with a velocity of 30 meters per second. So specifically, we can call that our initial velocity. And then it gives us a time in which it's stopping that is equal to 0.01 seconds. So what is the average force applied to the ball? So usually we would want to use our equation F net equals ma. But we only have the mass. We're not given the acceleration. So we're going to have to find our acceleration. So if we remember from earlier on in the year, we have the equation acceleration equals change in velocity over change in time. So if we're doing this, we'll break open our change in velocity, which is going to be final velocity minus initial velocity, over our change in time, which is just going to be our t. So we can get rid of that. Okay, now it doesn't say explicitly what our final velocity is, but what it does say is that it is stopped, which means that it's going to come to a rest, which means our final velocity is going to be 0 meters per second. So we can plug those values into our acceleration formula. This is going to be 0 minus 30 meters per second over a time of 0.01 seconds. So this will give us an acceleration that'll be equal to negative 3,000 meters per second squared. So it's coming to rest very quickly. All right, so that's a very quick acceleration. Let's see what that means in terms of our force. So we can plug it into our net force equation. F net equals our mass, 0.15 kilograms, times our acceleration of 3,000 meters per second. And we can include our negative. That's pretty much just saying which direction it's occurring. So when we plug that into our calculator and see what we get, you'll see that we get an answer equal to 450 newtons. So that's how we would solve that problem.